Welcome to the lecture series on electronic devices. So we are into the module 5 where we will be uh, studying about ICs, that is integrated circuits, in second half of the module 5. In the previous lecture we have seen the topics like photolithography, etching and metallization. So today's agenda will be the ICs, background of ICs, evolution of ICs, right? So, as a part of revision, let me quickly summarize what we have seen in the previous lecture. So, we have seen photolithography, the process of applying the photoresist, right, on the silicon dioxide, right? So, this is silicon dioxide, and this is photoresist, and then using the mask and through the mask applying the UV radiations. That process is called as photolithography. Right? So as we have seen, photoresist, they are of two types, positive and negative. Right? So we can remove the exposed part. Exposed part means the part which is being exposed to the UV rays. That part also we can remove, or the unexposed part, that also we can remove depending on the photoresist. So we had also seen the length of the transistor, it is in terms of nanometers, right? So at particular point of the transistor we need to focus the light. That means say 1 nanometer or 2 nanometers, only in that region we have to focus the light. Or you can say that the mask which has some holes, right, which has some pathway for the UV rays, right, those pathways should also be in such particular nanometers, very very minute, right. For that we require very precise equipments, and we have seen the arrangement of these equipments in the previous lecture, right. So photolithography, it is a repeated process in the process of fabrication of ICs or integrated circuits. Then we went through the etching, where we saw wet etching was used in the previous days, but nowadays we are using plasma based dry etching, right, where plasma radicals and ions, they are being bombarded, correct, and because of that the unwanted particles will be etched away, right, and we use some hydrofluorocarbons uh, as the etching gas also, so which helps in the etching, and we maintain the potential difference so that the kinetic energy of the particles which are being bombarded will be maximum. So here we have RF power supply. You can say that anode and cathode are maintained in such a way that the difference between those anode and cathode will be around 100 degree, 100 voltage, right? 100 volts. So voltage difference will be around 100 volts. Then we went through metallization, where we know that metallization means applying the metal on the material for the external connection. So for that we just use the wafer, and then the argon ions, they are being bombarded in the aluminum target, where the because of bombardment of the argons, the aluminum atoms, they just try to escape out. So this part is zoomed here. Okay, so this part, it is zoomed and it is shown here. So how the ions, or how the particles are moving because of bombardment of the argon ions. The aluminum atoms, they just try escaping outside because of that energy, and those aluminum, they will just stick on to the wafer, right, wherever actually it will be sticking throughout the wafer, but we again go with the photolithography to remove unwanted part, like everywhere there will be aluminum, okay, but we don't want the aluminum to be present on everywhere. So what we do, we just try to etch away again wherever aluminum is not required. We just try to etch away it using again photoresist mask and UV radiations. So this was the topics we had covered in the previous lecture. Coming to today's topic, that is about the integrated circuits. So what do you mean by integrated circuits, or what do you mean by ICs? Right? IC, basically IC is nothing but a circuit, or any digital circuit or analog circuit, like any circuit which is present on a single chip, or which is present on a single platform, right? So everything is integrated there. Say maybe AND gate, right, or OR gate, or multiplexer, right, or decoder. If all these different logic gates or different logic circuits are present on a single platform, right, that then we say that there is integration of different circuits onto single platform, right. This I took the example of digital circuits. Similarly, we may have in analog, we may have amplifiers, resistors, capacitors, right, filters, voltage regulators, all will be present on a single chip, right. Then we say that everything is being integrated on a single platform, right. So those are called as integrated circuits, or ICs in short. So black color ICs we usually see in the labs, right. Those ICs are for you can say educational purpose, right. So in IC we may have only four AND gates, or six AND gates, or in such a way, or six or NOT gates, right. Those are for just educational purpose. But in the same IC, as I said you in the previous lecture, there may be thousands of transistors, right. So how that IC concept has come and all, we'll study in the this lecture. So first, I said you what is IC, right? Everything integrated on a single chip or single platform, it is called as IC in electronics. And why we have to go with the IC? What is the use of that IC, or what are the advantages of IC? So first, very uh, important advantage, it is reliability and inexpensiveness, right. Reliability means what? That IC should be reliable. We can uh, believe that, right. We can depend on that for for our functionality, right. And what is inexpensiveness means cost effective. How it becomes cost effective? We'll see. Further, we'll see how it becomes cost effective, right? And huge numbers can be generated from a single wafer, right? So usually what happens? Here I have written 12-inch silicon wafer can be used. 12 inch is not a bad dimension, right? 12 inch means what? Almost you people have seen the laptops, right? That laptop screen will be 15.6 inch, correct? So slightly less than that laptop screen. That much big CD type silicon wafer can be taken for fabrication, right? And there may be hundreds of ICs, say 200 or 150 ICs can be fabricated using single silicon wafer, right? So, how it is becoming inexpensive? See, all the procedures which we are following for fabrication, maybe photolithography, etching, right, metallization, oxidation, diffusion, ion implantation, whatever we have studied, all the process, right, it has to be carried out for each IC, correct. But what we are doing, for each circuit, for each integrated circuit, we have to follow all those steps, correct. But what we are doing, we are using a larger silicon wafer and doing the steps right? Repeating, I'll be following all these steps for at once for an entire silicon wafer. That means what? If I do all these steps only once, then all the 150 or 100 ICs which are present on the silicon wafer, they will be ready. Okay, so the masks which we use, like all those should be having the pre-arrangements. Prerequisite should be satisfied. That's it. But all those steps, they are costlier steps, right? And if somebody says that, sir, following all these steps, I'll manufacture only one IC, then it is waste of time, waste of money, waste of material, everything is wasted there. Why? Because when you can manufacture hundreds of chips at once by following these steps only one time, then that is more advantageous, right? Hence, what we are aiming here, a larger silicon wafer, if we choose, the number of ICs manufactured or fabricated will be too much, right? With the same cost. If somebody tells us that I'll take silicon wafer of only 3 inch, if somebody tells us, the next person tells us, I'll take the silicon wafer of 8 inch, and if the third person says that I'll take the silicon wafer of 12 inch, right? Then the person who is manufacturing ICs using 12 inch will be more advantageous. He will be having more profit. Why? Because see, the process cost, say if it is 1 million, okay, 1 million, then this person will be manufacturing 4 to 5 ICs with the cost of 1 million. Correct. All the steps he will repeat. He will be doing all the steps, following all the steps, right? But when we come to 8-inch silicon wafer, then he or she will be manufacturing say 20 to 30 ICs or 40 ICs, right? With the same cost, with the same cost. And if I take a larger silicon wafer, then I can go with 100 ICs. 100 ICs again with the same cost, 1 million, right? So, what I'm trying to say, if we go with the large scale production, then it will be more cost effective. Cost will be less, right? So all the ICs, they will be formed, they will be manufactured in the batch. Okay, we see batch number for all the products, right? In the same way, in a batch or on a single silicon wafer, huge number of ICs can be manufactured or fabricated, right? So next point is same processing steps for almost same circuit, right? So as I said you, the processing steps will not change. Photolithography, etching, right? Diffusion, all these steps have to be followed for all the circuits, all the ICs. So steps will be same for all the ICs, right? Then I said you, taking a larger silicon wafer will give us better results. Huge number of ICs can be manufactured in the same processing steps with the low cost. Means cost will reduce if the IC's number is increased. Then the next advantage is tiny size. Tiny size means what? The small size. How we can go with the small size? Say we have to build a room, right? We have to build a room using say 100 bricks, right? This is fixed. Number of bricks will be fixed, 100 bricks. If you choose a larger bricks, then your room will be having larger size, correct? But if I choose a smaller bricks, right, then the size of the room will be smaller. Similarly, bricks can be compared with the components. Say if I need to make an adder, if I need, say for example, 12 gates, okay. If I require 12 gates for manufacturing or for fabricating an adder, then if the individual gates will be having lesser size, then the overall size will be lesser, right? So tiny size, if the sizes are small, then the overall circuit will be small. And next is low power, right? Low power means what? When the size is smaller, then the power consumption will be less. Say, even I had explained you this earlier. Say there are two transistors, right? In one transistor, the current will flow only for with the length of say 5 nanometers. Means the current will flow from one end to the other end, and the total length from one end to the other end is 5 nanometers, correct? And here, say here I have 100 micrometers, then it makes a huge difference. Current has to travel up to 100 micrometers, correct? And when current travels for a larger distance, its current will not remain same. Why? Because we know what is resistivity. Resistance depends on the area, right, and length. So resistance increases with the length of the material and it reduces with the area. So if we are increasing the length of the material, that means resistance of that material will be more, right? So 5 nanometer material or transistor will have lower resistance compared to the resistance of a larger transistor or larger material, right? And what is power? Power is nothing but, power formula is I into V, right? Or what is V? Again, if I go in detail, what is V? V equals to I into R, correct? So this resistance, if it is increasing, correct, the current will decrease. Or you can say, if resistance increases, we have direct relationship. Power increases when resistance increases, correct? Hence, tiny size transistors or tiny size materials will be consuming lower power, correct? When power is lowered, right? When the power consumption is less, then heating will be less. And when heating will be less, the electronic gadgets will have a longer life cycle. Why? Because the enemy of the electronics is heat. Every electronic device, it will get damaged only if it is overheated. Okay. If it is not overheated, it will run for a longer time. Right. So this is one of the advantage. In ICs, we have to follow this tiny size. For what is the result of that tiny size? Low power consumption, increased speed. I said you, current traveling for a shorter distance and current traveling for a longer distance. It makes the delay a major factor, right? So for traveling a longer distance, it will take a long time. So increase the speed, which is the need of the day. You can't wait for a computer to start up to 10 minutes. Right? If you start a button, you expect it to be powered on within few seconds. That is possible. Why? Because of this ICs and tiny size. Okay. Then no minor defects or less, I should write less minor defects due to soldering is seen in components connected on a board, right? So here what I am trying to say is, say if you just take a board and there you try to connect some resistances, capacitances, all the materials, all the devices, right? All the components, diodes, resistors, capacitors, and if you try to solder it, it will take like there will be some errors in soldering, right? But here in IC fabrication, everything is automated, right? So there will not be any issue related with soldering and all. The connection will be perfect, right? And by chance, if there is any minor error also, right? Few components may get damaged. Few components in the sense, if there are 100 ICs on a silicon wafer, and if some part of the silicon wafer it has not got proper lithography, right? Then only these many circuits ICs will be wasted, not the entire wafer. So everywhere the photolithography, etching, everything is perfect. Only at this part it was not perfect. There was some error. Then only 4 or 5 ICs which are being covered in this area will be getting damaged. Rest the other circuits they will be working fine, right? So what I am trying to say, on a silicon wafer, if we are manufacturing AND gate, then every gate will be AND gate. Okay, every circuit will be AND gate. it is a like a batch of AND gates, right? So out of 100 AND gates, maybe 10 may not work, right? But 90 will work, correct? So again, it is advantageous only. Why? Because I can produce 90 AND gates using the same cost, correct? And if it would be the best part if you can increase this number. If you can produce 200 or 300 AND gates, then it will be more advantageous, right? This is the technique being used nowadays. So we people are getting the electronic gadgets at a lower cost. Day by day, the cost is decreasing. Earlier, say if you go back to 5 years down the line, say way back in 2015 or 14, right? You would have to pay a huge amount for any mobile which was having the same features as of today. There was huge difference in the cost. So say 50,000, right? If any with some features, if any mobile was available with 50,000, but nowadays if you compare, it is around 10 to 12,000 it is available, right? So that is, everything is possible because of advancement in technologies related to fabrication. Then low weight, right? As I said, if the size is small, then the weight will be also be small, and especially in military applications where weight plays an important role, right? Like aircraft, rockets, jets and all, right? There, this low weight plays a very important role. And because we are into integration, right, ICs which are having a small size, obviously the will achieve this aim also, that is low weight. And quick replacement is also possible. Say if you want to replace an IC, right, which has damaged, right, which has been damaged, then that replacement is very easily possible. You can go with this, go to the service center, and the technician will just replace that IC. Everything is fine. Only that IC has to be changed, right? That person will do it. Then we have many applications on a single platform. Means what? Multiple applications on a single platform. Like we have a chip, right? On that chip there may be calculator. On that chip there may be timer. There may be alarm. There may be counter, right? On that chip there may be adder, subtractor, everything, multiplier, divider, everything will be possible on that single chip. There may be some memory to store the things, right? So multiple applications are possible on a single chip nowadays, right? So that is one of the greatest advantage of integration. Earlier, what we used to have, we used to have a separate IC for adder, separate IC for subtractor, separate IC for memory, right? Separate IC for analog to digital converter, and digital to analog converter, right? All these ICs were different, and we used to connect them externally, right? When you go with the older versions of microprocessor, right, you would have seen such cases. But nowadays we have very smart IC wherein everything is incorporated on it, right? All these are present within a single IC. Next advantage is good yield. Good yield means, I said you, if you are increasing the total number of ICs which are being manufactured, then definitely it will give you good yield, right? By just repeating that steps only once, you can manufacture thousands of ICs. If the IC's size is small, you can manufacture thousands of ICs. Am I audible? You people are understanding, right? Understanding? Yes or no? Next, we have types of ICs, that is, different types of integrated circuits. When we broadly classify, based on the applications, we have two types: linear IC and digital IC. Like linear IC is like analog ICs. Like that linear IC works on linear applications. That is, it works on different types of signals. Right? Say for example, op-amp, it is a linear IC, correct? Some amplifier ICs, they are linear ICs. But we have one more type which is digital IC, and that digital IC works on the logic 0 and 1, high or low, okay, on or off. That's it. So memories, right? Usually digital ICs, most of the digital ICs, they are being used in computers, calculators, and all, right? But linear ICs, most of the applications are being used in the signal processing, where analog signals has to be processed. Then depending on type of fabrication also, we can classify the ICs. So fabrication means what? Depending on fabrication means we may have monolithic IC and we may have hybrid IC, right? Monolithic IC means what? One platform. Monolithic means what? Mono means one, right? So on a single platform we may have all the circuits. Like I said you, we may have adder, subtractor, multiplexer, divider, AND gate, OR gate on a single IC, right? Then that type of IC we can call it to be monolithic IC. And monolithic IC, as I said you again, they can be manufactured in a batch. Right? Similar ICs can be manufactured in a batch, right? The ICs will be same. There will be a replica of each other, right? But all these ICs can be manufactured at a once using a huge silicon wafer, correct? So these are the monolithic ICs. What is the advantage in monolithic IC? They are cost effective. Why? Because more number of ICs can be manufactured. Identical ICs can be manufactured, right? And the other is hybrid IC. In hybrid IC, one or more monolithic or individual transistors along with the passive elements can be used. Like hybrid IC means what? There is a hybrid IC where I am using this one monolithic IC, correct? So this monolithic IC I will be using. Then I may use one op amp, I may use one resistor, right? Then I may use one capacitor, I may use three diodes, correct? Then I may use LEDs, correct? So it is mixed of everything, right? That is called as hybrid. Hybrid ICs, one or more monolithic ICs or individual transistors. I may have individual transistors also here, correct, surroundingly. And different passive elements like RLCs, resistors, capacitors and inductors, they can be fabricated on a single hybrid IC, right? Hybrid means what? It is mixed. Mono means what? It is one, all in one, correct? So hybrid may have monolithic in it. Okay, hybrid may have monolithic IC in it. Correct. Then what is the use of hybrid? See, it will be less expensive when it is done in small numbers. Okay. Why? Because it is not manufactured in a batch. No. We have to integrate it separately by placing different components, right? The components may have different things here. It may have resistors, capacitors, different types of components are there, passive, active and all, right? So it will be less expensive when it is done in small numbers. But here it is opposite. When it is done in large number, then only it will be effective. That is monolithic, correct? Then let us move to evolution of ICs. What do you mean by evolution? Evolution means it is like birth of ICs or how ICs were started. How did they start, right? So in 1959, Jack Kilby of Texas Instruments. This is the name of the scientist, Jack Kilby. Texas Instruments. It is the name of the company. So this person was working in this company, Texas Instruments. In 1959, he just tried to make an IC, right? Then we saw planar version of IC in 1959 only with this Chairfield. Uh, Planar version of the IC in 1959 uh, with this company, that is Fairchild company. And then Intel is again another company. Intel Intel's employee Gordon Moore, right? He was working in that Intel. He proposed a law which is very famous in VLSI. It is called as Moore's law. What is that Moore's law actually? So way back in 1960s, he had predicted, he had given that law, which is called as Moore's law, right? He said that on every 18 months, right? Every successive 18 months, the number of ICs and the number of transistors or the number of components which are present on that IC, it will go on doubling. He just predicted it, and it is true till date, right? Today also that is true. Means, uh, say I have 1 centimeter square, okay, 1 centimeter by 1 centimeter IC, correct? If in 1960, right, if there was only one transistor, correct, then what will happen after 18 months? After 18 months, on that same IC, we may have two transistors. Then after next 18 months, we may have four transistors. Next, after 18 months, we may have eight transistors. Correct. So this size of the components, the number of the components on the same IC, it goes on doubling for every 18 months. This was the prediction of Gordon Moore, and fortunately it is being validated. It is true till date. Okay, every 18 months, yes. That means what is the meaning of this? Components getting doubling. Yes, components getting doubled for every 18 means 18 months means what? Component size is getting decreasing. Yes, earlier if transistor was of 1 centimeter, then with the next version, the size was reduced. Hence, on the same area we could accommodate two transistors. For next 18 months, again the size of the transistor was again decreased. Right? So it is nothing but size of the transistor or size of the components getting decreased, or we are saying number of components on the same area getting doubled, increased after every 18 months. Okay, this is very famous law given by the Gordon Moore. Okay, very important. Then we had in evolution we had first SSI, MSI, LSI, VLSI, ULSI, RLSI and all. What do you mean by SSI? SSI is nothing but small scale integration. Okay, small scale integration means, right? Bringing all the things on a single platform. Okay, when it was done in very small scale, small scale means maybe 1 to 100. Okay, maybe on a single chip, if we have up to 100 transistors or 100 components, then it is called as small scale integration. Right? This integration is in small scale. Then what is next one? MSI. MSI maybe we may call this integration to be MSI when there are 100 to 1000 components on a chip. Okay, up to 1000 components, from 100 to 1000, maybe 500, 600, 900, 1000 components. If there are 1000 components on the chip, then we say that integration is MSI. Okay, then what is LSI? LSI is nothing but 1000 to 1 lakh. Okay, 1000 to, it is 1 lakh, 10 raised to 5, sorry, here, okay, 10 raised to 3 to 10 raised to 5, so it is 1000 to 1 lakh. Okay, so if 1000 or more than that, up to 1 lakh transistors or components are there on that IC, then we call it to be LSI, that is large scale integration. Okay, then if we have 1 lakh to 10 lakh components, then it is called as very large scale integration. 1 lakh to 10 lakh, then it is called as very large scale integration, that is VLSI, correct? Then ULSI means what? 10 raised to 6 to 10 raised to 9 components on a single chip, means it is 10 lakh to maybe 10 crore or 100 crore. Okay, so 10 lakh to 100 crore. If those many components are present on a single chip, then we call that type of integration as ULSI. It is ultra large scale integration. Correct? And above, more than that, it is ridiculously large scale integration. R is for ridiculously. If more than 10 crores or 100 crores of components are present on a single chip, then it is called as RLSI. It is ridiculously large scale integration. All this is possible because of only one concept, that is ability to shrink. Shrink means what? Scale down. Scale down means reduced in size. Okay, so transistor size is getting scaled down. It is transistor size is getting reduced day by day. Okay, so we are able to achieve this scale of integration. From SSI we have reached up to RLSI. Correct? No doubt there are technical challenges. It is not so easy to move from SSI to RLSI. You can imagine 10 transistors on a single chip up to crores and crores of transistors on a single chip, right? There is huge amount of technical challenge which is involved here, right? But it is an opportunity also. Okay, it is an opportunity also. Why? Because if we satisfy that technical challenge, then we are enjoying today with the electronic gadgets, right? And scaling, it is advantageous. I said you, what is scaling? Scaling is reduced size of transistor, right? How it is advantageous? I said you in the previous very first slide, what are the advantages of IC? That itself is the advantage of scaling. Low power, high speed, yes, lesser area, lightweight, correct? Low cost. All these are advantages of scaling, right? But what are the challenges? Challenge, very big challenge is clean environment. Adder and subtractor using decoder. Decoder. Okay. So clean environment and clean equipments. Okay. All the automated machines, they should be very clean, right? So this is one of the biggest challenge. Why? Because if any small dust comes in between the fabrication, then you can think that that batch will go wrong. That batch will be having maximum number of damaged ICs. Okay, and to satisfy that, the fabrication rooms, it will cost up to $10 billion. This data I am telling, it was for 2014. In 2014, if you want to make a room, fabrication room, then for one room it used to cost $10 billion. Getting? So there are few facts and uh, things which we have studied about the ICs, right? So IC, it has made the life of the man very easy, so easy that on a single platform you are able to enjoy the things. See, if you have mobile, yes, if you have mobile, then it is almost that you have everything with you. You have GPS, you have GSM, right? Where is your location, that you can identify. You can send a message anywhere throughout the world. You can call anyone. You can have alarm. Yes, earlier people used to keep separately the watches for alarm, right? The clocks for alarm. But nowadays everything is integrated on the mobile. Calendar, it is present. Reminder, it is present. Yes, each and everything is present in the mobile. Data transfer, any file, any video, any image can be sent within seconds. Right? So everything which we are seeing, it is nothing but the magic of technology, right? Technology has grown in such a way that we are enjoying today, right? And everything, it is nothing but uh, it is related to the IC only. Okay, everything, the heart, the electronic gadgets heart, we can call that it is IC. Okay, if there is no IC, there is no electronic gadget. Right. So this was all about the IC, and this is about Moore's law. I was saying that every for every 18 months, size of the transistor is decreasing in such a way that the number of components, it will double for every 18 months, right? So here they have given few processors in in 1970s. Okay, in around 1970s, there was a processor, Intel's processor, which was named by 4004. Okay, that processor, it was having say some 10 raised to 3 to 10 raised to 4 transistors onto it. Means what? Maybe say few thousands, say 5,000 or 3,000. If we exactly count, right? If we exactly count, it is around between 1,000 to 2,000 or within 3,000. Okay, so 3,000 transistors were present in 1970 on a processor, correct? But if we go with 1990, say here, okay, say here at this point, so 486, this is also one processor, correct? So here in 1990s, what we are seeing, so this number is around 10 raised to 6. 10 raised to 6 means it is more than 10 lakhs. 6 zeros I have to put, means yes, it is 10 lakhs, right? So 10 lakh transistors are present within 20 years. What was the count? It was less than 3,000, correct? Within 20 years, we are seeing this growth, right? And you come to 2010, right? You come to 2010, it has reached here, means it is in between 10 raised to 8 and 9, almost it is near to 10 raised to 9. 10 raised to 9 means what? Again I have to include 3 zeros, right? So it is around crore, 10 crore, 100 crore. Around 100 crores of transistors may be present in 2010. But now in 2020, it is more than 100 crores, maybe 1000 crores, right? It is 10 raised to 10, means 1000 crore transistors on a single chip. You can imagine how the technology has developed, right? And this is the Moore's law. This graph is indicating Moore's law. It is telling how the number of components on the same chip, it has increased or doubled for every 18 months, right? So this graph is very important. So even whichever we have seen, right? SSI means what? Few hundreds. Then MSI, LSI, VLSI. We have crossed all these things, right? Even we have crossed the ULSI also, correct? So we are advancing in technology with a very rapid rate. Then we have one more graph here, which is telling us feature size. Okay, feature size means what? Size of the transistor with the year. So earlier in 1970s, the size of the transistor was large, correct? So it is in micrometers, right? So this is 0.1, 1, and here it may be more than 1, right? Say maybe 10. So 10 micrometers. 10 micrometer was the size of the transistor in 1970s, correct? But in 1980s, it has come around 5 micrometers or 2, oh sorry, 2 micrometers, correct? Then in 1990s, it has come around less than 1 micrometer, right? Here we have 1. So less than 1 micrometer was the size of the transistor in 1990. Again, technology has advanced. In 2000, we had near to zero point 0.1, yes, near to zero point 0.1 micrometers. Then in 2010, the size of the transistor became lesser than zero point 0.1 micrometers, correct? And in 2020, right, it is very, very less, right? It is very, very less, means it may be around point, it is coming near to zero point 0.01 micrometers, right? Zero point 0.01 micrometers means what? It is 10 nanometers, correct? But now in 2020, the Samsung is working on 5 nanometer technology, or even the Intel is working on 7 nanometer technology, correct? Means what? 7 nanometer technology means size of the transistor is 7 nanometers, length of the transistor is 7 nanometers, right? So this graph is telling how the transistor size has decreased, and the Moore's graph, it was telling how the number of components has increased year by year. Understood? Okay. So we are into this understanding level in Bloom's law taxonomy. Thank you for your